Hi everyone, we are back, and now we are going to get into intermolecular forces. So these are weaker interactions. So as we saw for intramolecular interactions, they were all greater than 1 kT. So they could not break and reform basically at room temperature. But intermolecular interactions, as opposed to intramolecular interactions, are much weaker. And they're very, very important for soft matter systems, but specifically polymers, composites, and a lot of those materials. So there are lots of intermolecular interactions. We list some of them here, but the key thing is that, again, all of these have energies on the order of a kT or less than kT. So thermal fluctuations can break these bonds. So they are basically dynamic bonds. They are basically can break and reform at room temperature fluctuations. So let's look at some of these intermolecular interactions. So one kind of ubiquitous one is hard sphere potential. So again, atoms basically occupying space. So again, it's a quantum mechanical effect of nature. It's basically atoms will repel at very short length scales because they can't occupy the same space. Colombic interactions. So again, this is kind of electrostatic interactions between charged ions. We've talked quite a bit about the Lennard-Jones potential. So this kind of induced dipole interaction. So these are the kind of like fluctuations of electron clouds that will allow kind of these transient attraction and then repulsive forces as well. Hydrogen bonding, very important, critical to life. When will you have hydrogen bonds? Whenever you see this amide group, this is called an amide group, you will have hydrogen bonds in that polymer. You could also have hydrogen bonds in water. So an oxygen here, H2O, Gatorade, H2O. I'm going to get striked. But anyways, so hydrogen bonding. Hydrophobic effect. So you'll see this quite a bit. Hydrophobic surfaces. You've probably seen that commercial, or actually that company that made the ketchup bottle where it just slid out. Probably most famous hydrophobic. This is a cell membrane. So you have an amphiphilic molecule in your membrane. So these are hydrophilic heads, hydrophobic tails. So the tails are made of CH groups that don't want to interact. These are kind of phospholipids, basically that are charged. They want to interact with water. So you can have hydrophilic or hydrophobic interactions, and you can kind of have those interactions as well. Van der Waals forces. This Van der Waals forces, again, it's this kind of quantum mechanical effect in nature. The forces decay as d to the -6. So as my atoms start to get further and further apart, or intermolecular interactions become further and further apart, those forces decay quite fast. So they're going to be weak. But Van der Waals, it encompasses lots of different interactions. London dispersion, Debye forces, Keesom forces. Again, fluctuating polarization, nearby atoms. It's quantum mechanical in nature, but those are all, actually some, you could have ionic interactions as well. These are some of the intermolecular force interactions that we'll be talking about in this class. So, next time we're going to get into structure. We'll cover 2D lattices, and then we'll go through BCC, or simple cubic, BCC, and FCC structures. So we'll see you all next time. Thanks. Bye.